Hey, what's going on, guys? Coming again here. In this video we're going to be talking about serial communication between the Arduino and computer, but I'm using the virtual Arduino, and here we have the virtual serial monitor, but the idea still remains the same. So just a few words about the project to give an idea what kind of serial communication are we talking about here in particular, and then I'll demonstrate how this works, and then I'll walk through the implementation, which is very simple, but I've been searching for this solutions on internet, but I didn't really find lots of information about that. So eventually I came up with implementing things on my own. So probably this potentially might be useful to someone who would be trying to do something the same. So I'm building an 8-bit computer. So literally what this monster is. We have the LCD connected to Arduino. Well, actually I have Arduino Nano, but here in the emulator I'm using Arduino Uno because this is the only one available here, but they are compatible, the pin compatible, and literally the same, just the size is different. I've used the starter template that does connect the LCD already, so 16 characters, 2 lines LCD, and also I've manually attached, this keypad, 4x4 keypad, I've attached this manually, right? So what this thing can do, just probably better to give you an idea. So if I just input the address, let me just zoom this a little bit. So if I say input the address, and then I can input like whatever bytes, it just stores this, and if these bytes are the valid machine codes for the emulator that runs here, so here are the opcodes for the imaginary CPU emulator that I've created. So if these numbers are the valid opcodes, then if I use the run command, it would execute things, but in my case, it's just this is just a gibberish, so it just gives me an error that's just a known opcode and things like that. So let's actually reset the computer, and the idea is the following. So the very first computer I had in my life was ZX Spectrum, and the problem was that I didn't have a tape recorder. So when I was typing the game from the book into the computer, I was a kid, around 7 years old. It took around from 2 to 3 hours to input a very simple game in BASIC, and then I was playing for 5 minutes, turning computer off, and if I wanted to play the game the next time, I needed to type this again, like from scratch. So since then, I was really kind of dreaming about having a sort of a communication between the computer and some storage device that could be something similar to what tapes did on ZX Spectrum, on Commodore 64, and that sort of computers. So what I did came up eventually with. So I've written a very tiny assembler in Python. This is the entire assembler, so it's really small, but it already supports the labels. So here I've drafted a simple program that just prints the ASCII characters. So just loading the instant value to the A register. It has 2 registers, A and B, then putting the value from A register to B register, then loading the value for ASCII character of 0, then printing this to LCD, incrementing whatever we have in A register, putting some debug information on serial port, comparing with the value we have here, and if 0 flag has been set, if these 2 numbers are equal, like in register A and register B, they're equal, we just then go in here, clearing the screen, and dropping back to the loop. So a couple of loops, so nothing really special. But now the main question, like what this video is about to answer, is how on earth do we put this program into this kind of computer? So this is how am I doing this basically? So here I have an assembler, so I'm running the command asm.py proc.asm. It just brings some extra debugging information because I'm still debugging this sort of a thing. So the labels actually being converted to the absolute 16-bit addresses. And here I have the bytes for my program, but obviously these are the ASCII characters. And here we're coming to the most interesting part, because I'm gonna be passing the ASCII characters to the serial monitor, and then the program, my computer, this computer is going to be translating these characters into like integers in order to run them. And that's the most interesting thing, because I just first let me show you how this works, and then we'll talk through we'll talk about the implementation. So now here on my computer I need to type in the command allowing to load the data, and now a serial port on this Arduino simulator is waiting for the input to be passed in. So here I want to pass the inputs. If I just grab these bytes and copy them and paste them in and then send, now it starts, now it kind of like loads the data into the Arduino, right? And once it's done, it just prints that it's done. And well, let's say if we, sorry guys, I just typed wrong key. I just need to type whatever to exit from here because I don't have that enough buttons to see to control this. Let's add the command fffc and 0000. So here already we have the machine codes that, so if you have a look, so here we have 01, 42, 03 and so on, 01, 42, 03, 01 and so on. But you need to bear in mind the fact that here we have here is the hex editor, right? And here we have integers, and here we have like ASCII characters. Well, actually, in order to being displayed properly, they do internally being converted to ASCII characters as well. But in order to, but in the memory, obviously the computer is not executing the ASCII characters. It executes the bytes that those ASCII characters actually represent. That's the key thing. So what I want to say now, so if I just input the command to run this program, it starts kind of working. Well, this is just the debugging information that I need to, so just for the easiness of the development. So you don't need to take care about this. Just prints to serial monitor. It's nothing special really. Now, what is and another thing, like why do I use this? And it actually allows to slow down the process so I can inspect how things are going on. So the idea is that currently the bytes that do represent the assembled program for my imaginary CPU that works here on Arduino has been transferred from the computer to this virtual imaginary Arduino, right? But it works for real, and that's the major thing that I actually wanted to demonstrate. So let me just stop the simulation because it's gonna be working forever basically. And here is the source code. Well, I would rather go to my code editor here. It's easier to show the code here. And yeah, hold on guys, just one more little thing. Just before I just wanted to show you how we can actually store the program from that is available in the computer, how we can store it back to like from Arduino back to computer. So let's consider if we just quickly run exactly the same application here, and paste and send, but I'm not going to be running it this time. Instead, so let me clear the monitor. Instead, I just want to save it. And now, let's stop the simulation. It would then start saving some, just the bytes, so nothing special really. And here, for some reason, why does it actually print? I've already ruined the format somehow, so really need to check this out. But anyway, the idea is that whatever we have in the memory in this computer, it just kind of sends the memory dump for the entire 1K of memory from the Arduino using via the serial monitor back to the computer, so you can actually inspect this sort of a thing. And yeah, I just did something horribly wrong with the output format. I don't know why is this so weird, basically, but let me quickly check this. I don't remember what did I do wrong there. Save in serial print line. Oh, why do I print serial AVI? I shouldn't be doing this, really. So let me quickly check. Let me quickly fix this, right? I just wanted to show that we actually can save our work and later reuse that, like send it back. So that's kind of the idea. All right, and now let's put it back. All right, yeah, now this is what I wanted to show you guys. So it prints exactly the same string as it was. All right, so like, yeah, it prints exactly the same string. You just trust me that this string is really the same. And again, like, it does convert the bytes to ASCII characters back. So the string that we had input here, so this kind of string, and this one, they are the same. So we can put it to the computer, to the Arduino, where this imaginary computer runs, and we can pull it back. And this is done by a serial monitor. And the core idea behind this, that it would have been nice, actually, to be able to pass the bytes directly back and forth without a need to convert them to ASCII characters. And if you're not using Arduino software or this emulator for this, well, say on Linux, I could have just do this, like just writing files directly to the USB device. That's pretty much all about it. So it's not a big deal. But just in order to make it like a bit more standard, because I really want people to use my computer one day when I develop it, when I release it finally. So yeah, that would have been nice to work from the standard Arduino IDE, which everyone is used to work with, right? So the idea is that we actually do use the ASCII representation, using ASCII characters to represent the bytes, just like the hex editors do, basically. And yeah, just know we don't have any spaces here, but it's not a big deal, really. Yeah, so it's just the bytes that we want to work with. So let's have a look how the implementation actually kind of works. So here I have two cases within the switch statement, and this so these are all the commands that my Arduino-based computer actually takes. And let's have a look. Let's inspect what happens when this load case occurs. So clearing the LCD, some cleanups, nothing special, right? And the most essential thing is here. So once it did print the message, like waiting for incoming data, what actually happens under the hood later on? It actually stucks in an infinite loop. Well, well, actually, this might be treated as an infinite loop. So at very least, this loop lasts until when the serial port receive buffer gets the data. So once the serial receive buffer gets the data, this serial available is going to be equal to more than 0, right? And in that case, we can actually start the loop that actually starts reading those bytes one by one, meanwhile encoding the ASCII characters to the actual integers. That's we're going to talk about this just right in the moment, right? So and before we step into the encoding and stuff, which is pretty trivial, I would say, I want to emphasize this line, which is the most essential one, and there are really tons of unanswered questions on forums related to Arduino, like how to read more than 64 bits or 8 bytes using the serial.read function, right? So the problem is that the input buffer on Arduino only contains 8 bytes or 64 bits, And people were wondering like how to manually reset the buffer, or how to make the buffer actually take in a new chunk of data and things like that, and no clear answers at all. Until once I find actually one question somewhere, I don't even remember where exactly that occurred. But anyway, so the idea is that actually we can make use of quite pretty slow, what is known as the baud rate. So baud rate is the speed of how fast the characters are being sent via the serial port. And again, like from the lower from the circuit level, what we have a pin that transmits the signals, and we have another pin that receives the signal. And the entire communication, well, if I'm not mistaken, this is known as UART protocol, which stands for Universal Asynchronous Receiver Transmitter, right? So the idea is that we just send in packets from one pin to another, and what these packets are, so ultimately these packets are just the combination of like signals like plus 5 volts, which is known as high, and like 0 volts, which is known as low, and then they just frequently flowing, representing the certain data, and the UART protocol actually handles that on that node. And the idea is that on the hardware level, what happens there is just we have like the receive on the receiving side, the buffer takes up to 8 bytes, and then when it gets full, the next byte that would be coming in would actually automatically clear the buffer, and the new chunk would arrive if it's already available. If it's not, it would be just populated byte by byte. So it doesn't really matter if you just do this like 8 byte chunk like once, or byte by byte. So until the received buffer is been fulfilled, it just waits for bytes to arrive. Once it's fulfilled, it just gets cleared automatically, and then we're waiting for a new chunk of data to arrive. And the trick and the hack is that we need to wait a little bit until this process kind of happens. And the hack is just to wait for 1 second. So once we read a chunk of data, we're waiting for 1 second, and until the new data chunk arrives, and that's pretty much all about it. And now you might be wondering why 1 second, and it's not a silver bullet, by the way, and it's only working with a 9600 baud rate, which is the slowest one. And 9600 baud rate is 960 characters per second, if I'm not mistaken, right? So and that's where the second actually comes from. So we just wait for a second, and then buffer gets cleared, it receives the new data, and then we just reading this normally. So like from the code perspective, all we do here, so this line actually calls serial.read. We'll now have a look at how that works. But actually every this condition is every 8 bytes, we want just simply to make this delay like 1 second delay. That's pretty much all about it. So this works like a charm with 9600 baud rate. So that's something that can be used with a success, basically. And when it comes to actually writing the bytes, it's even more simple. So here at Alero, just using serial.print, and we don't care about the buffers at all. We just print, receiving these bytes one by one, and it's already the problem of the software that is actually on the receiving side to handle all this stuff. But it does this automatically, so we don't really need to be bothered about this. So if we want to store something from Arduino, like pass it to the computer, we can just use the serial port, just the simplest possible serial print. That's pretty much all about it, right? So now let's have a look at another I would say important part, right? So what happens with this within this encode byte? So let's search for encode byte procedure, and here it is. Yeah, so I was forced to handcraft all of this stuff on my own, and actually before writing this in C, like the previous project when I was doing literally the same, but a little bit, but without Arduino. Let's say, yeah, the same thing, same project, but without Arduino. I was writing this in x86 assembly language, and I had a chance to work this out. So now in C, I'm just doing exactly the same thing that I've been doing in x86 assembly in my previous attempts. So it's very simple. So we're just creating the 8-bit or 1-byte value, unsigned type value, and then the next thing we do here, we actually so this loop goes twice, like it just makes 2 iterations literally. You might be wondering why I minus equals 4. Well, that's because that's exactly what we need. So here's how it works. So first of all, we need to take an ASCII character as an input. So you just bear in mind that here we do, so this 0 is just the ASCII character 0, which would be 48 in decimal or 13 hexadecimal, but this is just an ASCII character, so it's not 0, it's not really 0. So the byte actually the byte takes 2 characters. So every character should be translated from the ASCII to integer, and then it should be encoded as the nibble. Nibble is the half of the byte, and the bits representing that nibble should be placed properly. So I'm using bit shifts here in order to achieve that. So this function literally does what I've just said. It just converts the ASCII character to integer by subtracting either the value of ASCII character 0 or subtracting the value of ASCII character A plus 10, so that A would be translated to 10, B to 11, F to 15, and so on. So just to translate this ASCII characters to hexadecimal, either digits or letters. So once we've done that, this hex variable, it actually holds the single nibble. So nibble is the half of the byte, and then what we do here, so we say if I is equal to 4, and that's why this condition arises. So in case if I is actually not equal to 0, yes, it's equal to 4. We know that this is the first nibble that we're working with, and in this case, what we need to do, we need to take this nibble and left shift the bytes by the amount of I, and I is equal to 4. So we shift in 4 bits, not bytes, 4 bits to the left, and then we bitwise OR our value, which is 8-bit, right? So we have like 4 bits arriving here, and we have 8 bits value to store this. So and we just put them here like so. So the first character, the first ASCII character being converted to a nibble becomes the most significant nibble, I believe, right? So it becomes the most significant nibble, and then otherwise, what can happen? So if I is equal to 0, we are in the second stage. So in this case, we just bitwise OR the value with the second nibble, and this second nibble becomes the least significant nibble. And eventually, we're coming up with having 2 ASCII characters being encoded as the single byte. That's pretty much all about it. And then we just print. What am I doing here? Yeah, so yeah, just it's used. This function just used twice to encode bytes from the keypad. So if I'm pressing the buttons here, it actually passes in the ASCII characters as well. And another source of ASCII characters is the serial monitor. So this function handles both cases. It's actually used to convert the ASCII characters to the first ASCII character becomes the most significant nibble, the second ASCII character becomes the least significant nibble, and eventually 2 characters are being turned into a single byte. And that byte then gets printed to LCD if needed, if this is the keypad input, but generally just returns the value. And once the value has been returned, let's get back to our load stuff. So once the value has been returned here, so I'm just specifying whether I'm reading from the serial port, it's just the constant 0, and in keypad is the constant of 1. So if we're reading from the serial port, yeah, in this case, it's the same like in the case of the keypad. We're just not echoing the character to LCD. That's the only difference. And yeah, also obviously the difference is we're switching the source of where do we take where do we read our ASCII character from. So in case of a keypad, we're reading that from the keypad. In case of the serial port, we're using serial.read. And yeah, just probably worth mentioning as well. So here, in case if source is equal to 1, which is keypad, we're using this get character, a custom function that I've written here. So just stacks in the loop until user actually clicks some key. Once user has clicked the key, just returns the key. In this case, the ASCII character, right? And in case of serial communication, we just read a single byte. The next byte of the incoming data that we have, right? We're actually reading this from the receiver buffer, right? And yeah, and then we just no matter what the source is, we just need to keep track whether this is the first character or the second one, formulate a byte from that. That's pretty much all about it. Now when we load, so whatever has been returned by this encode byte would be actually the byte, and we then store that byte into the memory. So this is how the entire load command actually works. It's quite pretty simple. And yeah, and again, like when we're saving the byte, it's even simpler because we just can print this to serial port, and that's pretty much all about it. Okay guys, so this is it from my side. I hope you learned something interesting about how to communicate between Arduino and your computer via the serial port, and how to convert bytes from, like how to formulate a byte from two separate ASCII characters. And hopefully this is going to be useful. And from my side, I'm really happy to have this tiny little guy here would be allowing me to, like, so now I can actually code in the assembly that I've handcrafted on my own for my image reprocessor, right? And then I could just kind of assemble it, take the codes, pass them in, and then run the computer and enjoy the show. That's pretty much all about it. And yeah, hopefully tomorrow or the day after tomorrow, LCD and keypad should arrive, so I would be able to try to run this on the real hardware. Currently I only have Arduino Nano has arrived and the breadboard as well, but I also need obviously the LCD and the keypad. And once I got those, and once I build this computer, once I debug everything, there would be another video introducing the full-blown version of this Code King's computer. So hope you enjoyed that as well. Okay guys, this is it from my side, so thanks for watching. Until the next time, and take care.